Hello everyone, we will continue our lecture series in this optimal control guidance and estimation course. Last couple of lectures we saw this optimal control formulation from calculus of variations, and then we gave couple of examples which motivated that in general we need numerical methods to solve the nonlinear optimal control problems. So, let us see a couple of such techniques, numerical techniques. And then we will follow up with further things and all that actually. Alright, so the topics covered today in this lecture is first we just very briefly review the necessary conditions of optimality, then followed by we will talk about 2-3 methods, and then first one is Sooting method, followed by gradient method and quasi-linearization method actually. So, there are various other techniques as well, but it is not it is not necessary to continue talking about all the methods, but you can after knowing these techniques probably you can see some literature or book or something and then follow the other techniques as well. Anyway, so let us get started. So, this is the generic optimal control problem that we are interested in kind of optimizing or minimize or maximize certain performance index of this form. Okay, and along with the performance index we have this associated path constraint as well as boundary conditions actually. Okay. So, the necessary conditions of optimality that we derived in previous lecture turns out to be like that. We have a state equation which is x dot is del h by del lambda, which is the f of x sort of thing, which is coming from the system dynamics typically. Then followed by this co-state equation as well, which is lambda dot is minus del h by del x, and both of these happen to be differential equations, dynamic equations really. And then the third equation is optimal control equation, which is a static equation. For from this equation we are we should be able to solve for optimal control u as a function of x and lambda actually. Okay, so that is how it develops, but for these two differential equations we have these two boundary conditions as well. So, the problem is well defined really, and you can see that the state equation takes this initial condition, whereas co-state equation takes the final condition. Okay, that is how it is it lands up with these 2-point boundary value problems, and then these 2-point boundary value problems should account for all these boundary conditions properly. Okay. And also remember that if a solution does not satisfy any of these equations, any one of the equations including the boundary condition, that means the solution is non-optimal. So, we must cater for all the conditions, and we must cater for all the conditions with equal emphasis actually. So, that is the point there. Okay. So, this let us get started with before getting started with some of these techniques, we also discussed in the last class that the state co-state equations are dynamic equation, and it turns out that if one is stable, the other turns out to be unstable in general. Okay. The optimal control is a stationary equation from which you need to solve for control and for which we need to know the lambda. Unless we know lambda, we cannot solve it from here. Okay. And boundary conditions happen to be split. That is what I told you here, that the state equation has initial conditions, whereas co-state equation has final conditions actually. And typically because of this, the state equation typically develops forward, whereas the co-state equation should develop backward, because you know the final condition basically. So, that is why typically the co-state equation we can integrate it backwards, because we know the boundary condition at the final time. In general, the numerical techniques can circumvent some of these, and then talk about forward integration of both the equations and all that. We will just see that in a while actually. Okay, so all this difficulty that the boundary conditions are split, and if one is stable, other is unstable, things like that leads to this great difficulty of this complexity issues and all, and hence this particular feature that we are talking about is also known as curse of complexity in optimal control. So, you will end up with nice formulations, but as a necessary part of necessary conditions, we are leading towards this curse of complexity. And traditionally this 2-point boundary value problems require computationally intensive procedures, and we are going to see some of these classical techniques in a while anyway. But ultimately also remember that everything said and done, it ultimately leads to this open loop control structure actually. Why so? Because ultimately after we get the solution in iterative sense, we are getting a solution for a particular initial condition. If the initial condition is changed, then the solution is not valid. Okay. So, because of that, and once the initial condition is fixed for all future time T naught to T f, your control strategy also gets fixed actually. So, because of that, this has a feature of getting into this open loop control structure actually. So, these are some of the comments and difficulties associated with that. Alright, so let us proceed further and then talk about one particular method called suiting. So, this is a traditional method, very intuitive obviously, but it has its own problems as well. So, let us see what is the philosophy first, and again just to summarize, you have the state equation, co-state equation, optimal control and boundary conditions. Remember, once I solve this optimal control equation, okay, del S by del U equal to 0, then I can end up with this u equal to psi of x and lambda. Okay. So, in general you may or may not be able to solve it in explicit form. Okay. If you do not have, you are not able to solve explicit form, then you have to solve using these numerical techniques like Newton-Raphson method or things like that. But suppose many class of problems, it is possible to solve u as a explicit function of x and lambda. So, let us assume that it is solvable either symbolically or numerically, either way actually. Okay. Once you solve it, okay, you can, if necessary, we can put it back here in the lambda dot equation, and if necessary, we can put it back here as well actually. Okay. So, then this u will be eliminated from both the equations, and you will end up with x dot is nothing but x and lambda, which is a function of x and lambda, and lambda dot is a function of t x and lambda as well actually. Okay. Most of the time we will not discuss about this time dependency, but it is if it is I mean if it is there, then it is not a matter of concern actually, it can be handled directly as it is actually. Alright, so this boundary conditions, I told you that this is final boundary condition, this is initial condition. So, this strategy tells us that okay, let us be little more intelligent and have a guess for lambda 0 actually. Okay. So, how about starting with a guess? And again this I need to emphasize here that guessing a lambda 0 value is not a trivial task actually. It requires a lot of insight into the problem, or essentially it has its own tricks and techniques how to guess this lambda 0. And one way that I will recommend probably is you can guess a intuitive control history. Okay. You can guess from T naught to T f, and once you guess u naught, then you can probably integrate this equation, state equation, because x naught is available and your control history is available. So, you can integrate from T naught to T f using that particular guess control history. It is nowhere close to optimal in general. So, but use that control history because that is an intuitive control anyway. So, you can integrate this state equation from T naught to T f and get your x f, and once you get your x f, then you can get this lambda f. And once you get your lambda f, then you can using this condition, then you can integrate this equation backwards from T f to T naught now, and that is how you get a guess value for lambda 0. Okay. So, lambda 0 is not a trivial task because of several reasons like that, and one of the primary reason is lambda in general does not have any physical meaning. It does have some geometric meaning, we will see that later, but even geometrically it only gives some sort of a direction meaning, it does not talk about magnitude meaning. So, and lambda is not a physical variable, we cannot talk about position, velocity, current, voltage, nothing like that. So, we cannot really have a good guess for lambda in general. However, control is a physical quantity. So, we can guess the control history from T naught to T f, maybe using some stabilizing controller, PID controller, or just some heuristic controller from the problem definition itself. Okay. So, using that, or even sometimes I do recommend using zero control. If the system is stable, then simply start with zero guess history, and you can integrate the equation, the homogeneous equation, and then get it x f and then get it backward actually. That is also a possibility. But again, these are problem dependent. Once you start working on a problem, you will select a particular guess, all that. But the point here is guessing a lambda 0 is not trivial. Okay. So, give some special emphasis for guessing a good value of lambda 0. But once you guess it, okay, now remember, now for a while you can ignore this and then tell, okay, these two differential equations have a corresponding initial conditions available. Okay. So, I can take this initial condition and integrate these two equations forward, state and co-state equation forward, because u I have already eliminated in terms of x and lambda. So, these two are functions of x and lambda only. I have two differential equations, two sets of differential equation and two sets of initial conditions actually. So, I can use this and then integrate it forward. and then I will see that okay, once I land up there and t equal to T f, then that lambda what I am getting here and this lambda computed this way, okay, they may not be same, and they most of the time they will not be same. So, that is why we are telling like okay, but this integration process is something like shooting. I mean you are shooting a gun sort of thing towards a target, and finally it lands up somewhere with lambda f, but this the goal point is somewhere here lambda f, I mean lambda f is del phi by del f what it should be, and then we sense the error between the two, and using that error we have to come back and improve this lambda 0, that is the philosophy. Okay. How do you do that? I mean see that before that this is the procedure here. So, you start with some lambda 0, okay, lambda 0 for first guess sort of thing, and then start integrating forward T naught to T f, you land up somewhere, and then lambda f star happens to be somewhere here. Okay. So, use this delta lambda f, okay, what you have here, okay, this using this delta lambda f you have to come back and correct this lambda 0 1, okay, to lambda 0 2 and repeat the procedure. Maybe you will go slightly more closer, or maybe you will overshoot next time probably like that actually, but the iteration proceeds that way. Okay. So, to summarize, guess the initial condition for the co-state first, compute the control at each grid point, because once you have the in lambda 0 you have x 0. So, u 0 is nothing but function of x 0 lambda 0. Once you have u 0 you can get a u x 1 from here. Once you have once you have x 1 and lambda 1 as well, once you have x 1 and lambda 1 integrating these two equations together, you can calculate u 1. Okay. And then if you once you have u 1 you can calculate x 2 and things like that actually. Okay. Alright. So, compute the control at each grid point and then propagate the state and co-state equations, and then calculate the final boundary condition and error in the co-state at the final time. Okay. And then correct the co-state vector at the initial time based on this error at the final time. That is why I told you, and then repeat the procedure. Keep repeating the procedure until and unless this lambda f what you are getting from integrating this point is very close to what it should be. Okay. Then you tell okay, everything is satisfied, because I am starting with this initial condition of the state anyway, and then I am satisfied whatever integration I am getting for wherever I started I landed up there, these two values are very close. So, this is also satisfied, and I have used this control on the way anyway. So, this is satisfied, and these two equations I am integrating as a part of the procedure anyway. So, all the conditions will be satisfied actually. Okay. So, little bit math now, okay, how do you do that actually. Okay. So, this is what I recommend, that form a metastate vector x and lambda. That means instead of talking these two separate equation, we can always tell that as a function of x and lambda in a bigger state that we call as metastate vector, because u is already eliminated from here. Okay. So, then this implies that the error in dz is nothing but dx by d lambda. Okay. And this information is used in the linear equation setting basically. Okay. We will see that in a while. Okay. Once I define this metastate vector, what is z dot? Z dot is nothing but x dot and lambda dot, which is nothing but, if I go back to here, this is nothing but x and lambda sort of thing. Okay. So, this is what it turns out to be f of z. Okay. So, and associated with that z of t naught is now available, because lambda of t 0 I have already guessed actually. Okay. Alright. So, now corresponding to this differential equation which is nonlinear, we can also obtain a corresponding linearized error dynamics, which is dz dot is nothing but dx dot d lambda dot, which is nothing but equal to del f by del z into dz, using this Taylor series linearization ideas actually. So, we have this metastate vector differential equation associated with boundary conditions, and associated with this equation and boundary initial condition, we have this corresponding error dynamics as well. All these things we have to take advantage of actually. Okay. Now, if you have the point here is this we have a linearized version of aerodynamics, but remember that del f by del z is not a constant matrix. Okay. So, this matrix is certainly not a constant matrix, it is time varying matrix. So, we cannot write this closed form solution of e to the power at and things like that, we cannot do that actually. Okay. So, what is the usual way of time varying linear systems? We know that it can be written in the form of state transition matrix. Okay. So, we have this linear equation here, okay, but there is a time varying matrix involved here, and because of that the solution turns out to be something like that. So, dz at any point t j is nothing but phi of t j t I and the corresponding value dz of t I. Okay, that is how it proceeds this way. Okay, now if you have this form, okay, that means if you know the error at any point of time t I, you can calculate at any other point of time t j basically. Now, the corresponding equation the state transition matrix turns out to be phi of t j t I. And the dynamics and initial conditions, okay, now that we have written in this form, we need a solution or need a number for this matrix actually. So, this is very standard linear equation systems theory, and then if you write a state transition matrix, the same state transition, I mean the state transition matrix in general will satisfy the same differential equation, okay, whatever differential equation you have, but in the matrix sense. Remember, dz is a vector where phi is a matrix actually, but the differential equation turns out to be exactly same, okay, I mean exactly in the same form basically. So, you can take this df by dz and plug in here, it will satisfy this equation anyway. Okay, and then you have this phi of t0 initial condition is invariably identity, because if you see this equation, if it is t0 and t0 both are same, then this has to be identity actually. Okay. So, this so what is the beauty here, that irrespective of the problem definition, okay, or irrespective of the initial condition of the problem, this particular phi can be obtained independently actually from any t naught to t f. This is a differential equation and this corresponding I mean initial condition. Well, we need the information of del f by del z also on the way. So, that way it is coupled in a way where you are talking about, in which segment you are talking about, because the value of df by del f by del z can vary depending on that basically. But those details is, I mean aside, what happens is you have a state transition matrix and the corresponding initial conditions actually. So, this system of equation can be integrated and you get phi of t j t I. Okay. So, proceed further actually. So, what it tells us is you can now integrate this equation with corresponding I mean corresponding state transition matrix equation as well, okay, and from t naught to t f, and then you can start solving for the optimal control equation actually, okay, because once you know this actually, okay, then your solution is almost ready, because you know this I mean dz, okay. Once you know this dz of t I, then you can proceed further and then you can integrate this equation also in a way, okay. Once, because this equation and the corresponding initial conditions are available. Similarly, this equation and corresponding initial conditions are available. So, this set of equation along with this set of equation can be integrated forward, okay. Once you integrate it forward, then you can compute this thing, okay, at any point of time basically, okay. Alright, just using this differential equation, just using this algebraic equation, because the solution of this is now available from this set actually, okay. Alright, so this is the thing, and then finally what we will get, okay. Right. Finally, what we are getting something like this actually, at t equal to t f, dz f, okay, by definition is dx f and d lambda f, and this is simply if you put it here, you will get it phi of t f t 0 dz 0. Okay. Now, the question here is we are actually interested in getting a value for dz 0, because what you know is dz f actually. Okay, ultimately what you will know is because lambda f will be embedded in lambda f, I mean dz f will contain a d lambda f term, and using that we will be interested to calculate d lambda 0. That is the whole idea there actually. Anyway, so coming back to that, this dz f is calculated this way, and hence in principle this dz 0 is nothing but this phi inverse t f t 0 dz f. Also remember, state transition matrix are never singular, and hence this inverse always exists actually, okay. So, this is always possible to compute. Now, the question here is we do not want to perturb this dx naught actually, right, dx naught is fixed and we want to preserve that. So, invariably no matter what we get from this solution, okay, that we do not want to consider that actually. So, we consider this dx naught equal to 0, we are interested only in updating lambda 0, okay. So, you can keep on doing that until some convergence happens and all that actually. But okay, this is fine, I mean if you can implement this way. However, there is a small computationally the procedure can be made faster by this idea. You can partition this state transition matrix this way, halfway, phi 1 and phi 2 exactly in the middle, okay, vertically. Then dzf turns out to be this way. You can write it phi 1 times dx naught plus phi 2 f times d lambda naught. Okay, you can this equation what you are looking for, this equation, okay, can be written in the form of phi 1 f dx naught plus phi 2 f d lambda naught actually. Okay. Now, we are interested in forcing this lambda dx naught is 0 anyway, that is what we just discussed in here. Okay. Okay. So, because of that this turns out to be 0 and hence we will end up with this. Okay. So, what you are looking for is now you tell, okay, for convenience we can think that h equal to some lambda f be the vector of n boundary conditions at f. That means, the way that you compute the desired lambda f, we can consider that as a function of lambda f itself. Okay, you can generalize this problem a little bit further. I mean, it can be simply lambda f itself, it need not be a function directly actually. Okay. So, anyway, so what I mean is this condition is available. Okay. Let me see that. Okay, this equation, right? This equation, this is available. Okay. So, using this now you can think, okay, I will consider that, I mean, call that as h or something there. Okay. Then you can tell, okay, d lambda d, I mean, what you are having here dzf is actually, okay, is nothing but del h by del z into dzf. Okay. Alright. So, you can do that and then that turns out to be a lambda f minus lambda f star, what it should be, and then you can substitute all that, okay, and then tell, okay, if I substitute it back here, okay, what I am getting here, okay, this dzf is I mean, okay, substitute back here and then equate it to, and then I can compute it this way actually. Okay. So, the whole why it is so, because see the here we think about doing that directly, then this will end up with a 2n by 2n I mean matrix inversion actually. Lambda is x is n and lambda is n. So, dz turns out to be 2n by 2n 2n by 1. So, phi turns out to be 2n by 2n. So, 2n by 2n matrix inversion is required, but here if you do this little bit algebra, it requires that it is this happens to be n by 2n and this happens to be 2n by n. So, that means you will end up with n by n matrix inversion only. Okay. And which is also logical, because all that you need is n dimensional correction, rest of the n dimension you do not need anyway, this is fixed to 0. Okay. So, you do this operation and then this just multiply these components together and then take the inverse, and then you will be able to compute it in a slightly lesser computational intensive way. Okay. So, it will just save the matrix inversion from 2n by 2n to n by n. Okay. Anyways, coming back, this is what it is. So, you keep on doing this exercise, you keep on computing d lambda 0 and correct your lambda 0 k to lambda 0 k plus 1 using this d lambda 0, okay, and then keep on doing that to repeat the procedure until convergence actually. So, this is how sorting method operates. Now, there are several problems in this method. Okay. First of all, as you might have noticed that this particular method is in general sensitive to the procedure. I mean, the sensitivity of the procedure to the initial value of the co-state actually, that becomes a major issue here, and that is very apparent also. Like if you guess a wrong value of lambda 0, it turns out to be sensitive. Okay. And it can be very misleading also, but the fact is if your initial state equation is or system dynamics is stable, then the co-state is actually unstable. So, any amount of different lambda 0 that it then other than that what it should be, then you are actually integrating an unstable differential equation numerically. So, the error is going to grow very fast actually. Okay. So, that is why it is sensitive to that. Okay. So, in general the procedure is sensitive to the initial condition guess value. Okay. Second thing is, as I discussed, co-states do not have physical meaning in general, and this complicates the issue of selecting good initial values actually. Okay. And I have explained the procedure, how do you do, I mean how do you do a guess value. and it is usually done through guessing a control history rather actually. Okay. And invariably you will end up with, I mean, all these classical methods and many of the numerical techniques you will requires that you guess a sensible control history to begin with. Okay. Then you update on that like that actually. Alright, so this is what I have already told. Co-state equation is normally unstable for stable state dynamics. Hence, in general, long duration prediction is not good actually. Okay. And suppose you have a unstable state, then also you have unstable system dynamics, then also you have a problem, because anyway you are integrating the state equation forward as well actually. So, either you integrate the co-state equation forward or integrate the state equation forward. If one is stable, the other is unstable, and hence everything is a very sensitive issue here actually. Okay. Anyways, what is the solution to that? This method is sensitive. So, one way is the policy of divide and rule. You do not have T0 to Tf because the integration error can blow very fast actually. And then all that you are saying here is linear philosophy. Do not forget that also. The error dynamics has to satisfy this linear equation dynamics and all that actually. So, as long as the errors are small, then this dynamics is valid, otherwise no actually. Okay. So, be careful about that. And so, the one idea is, okay, I will divide this segment time duration T0 to Tf to some 2 segments, let us say to begin with, or it can be in general multiple segments. Okay. Once I divide it to let us say 2 segments, okay, then I actually thought about, I mean, what is essentially needed is visualizing the problem as 2 different problems actually. One problem operates from T0 to T1, the other problem operates from T1 to Tf. But what it essentially the same idea is called multiple shooting, because you are not shooting all the way, you are shooting in a piece, I mean piece sense actually, part sense actually. Okay. Okay, but it also brings additional constraints of continuity and smoothness. So, even though this is only, remember these are all artificial division actually, but the problem is not like that. Problem operates from T0 to Tf in a continuous sense actually, and the system dynamics are typically non-holonomic constraints and all that we discussed before. The system trajectory is not going to admit any discontinuous or non-smooth trajectory and things like that. Okay. So, it is our duty to enforce that wherever you are splitting the problem, okay, we need to guarantee continuity and smoothness. Okay. That brings in additional constraints actually, okay, at the joining points, and this is possible, but it is also, I mean, do not keep on blindly applying and all that, that is the message there. Okay. But this is the whole idea of multiple shooting, and most of the time this multiple shooting approach is also extended further and further, and people talk about direct transcription method and all that. We'll see that I mean later in this course actually. Okay. But anyway, so this is the whole idea of shooting method as well as multiple shooting actually. Okay. Now, what about gradient method now? The second method. Okay. Remember we talked about, we intend to discuss 3 methods here actually. Alright, so now coming back to this, what is happening here? I mean, the whole idea here is propagate the state equation and co-state equation forward in one direction. It ultimately it means. But if you see these equations, as we discussed before, ideally the state equation should be integrated forward, whereas the co-state equation should be integrated back, and that feature is not there in the shooting method actually. Okay. Now, gradient method tries to exploit that feature, and hence in general gradient method turns out to be more stable actually numerically. Okay. Alright, so let us see what is gradient method here first of all. Okay, the procedure is same. We start with the initial guess value of the control history and then try to get the control history actually. Okay. So, with respect to the guess value of the control history, what you are assuming that if you use that control history as an optimal control solution, I mean in general, then we are assuming that that particular guess history or the previously updated history satisfies these 3 equations actually. It satisfies the co-state equation, it also satisfies the boundary condition. What it does not satisfy is the optimal control equation. Okay, that is our assumption actually. Okay. And because these are assumptions, you much better off by value which satisfies these equations anyway. Okay. So, start with a guess value which will satisfy these equations. Okay. And if you start with a state, if you start with a control history Okay, you start with some sort of a control history. Okay, T0 to Tf whatever. Okay, you start with a control history, and then you integrate the equation, state equation anyway, right, using this control history. So, obviously, the state equation is satisfied. Okay. Now, you can calculate some co-state final co-state using that, and then compute it. I mean come back actually. You starting with that final condition of the co-state, you integrate it backwards. So, the co-state equation is satisfied. Okay. And you are starting with the initial condition of the state, and you are using the boundary final condition of the co-state anyway. So, the co-state equations, I mean the boundary conditions are also satisfied. Okay. So, the ultimate what remains to be satisfied is the optimal control equation actually. Okay, that is the whole idea there actually. Okay. Okay. Alright. So, the procedure is like this: you guess a control history, and then start with the initial condition of the state, integrate it forward. Okay. And then at the end you calculate the required co-state using the final condition of the co-state, lambda f equal del phi by del x, that kind of thing. And using that lambda f and the co-state equation, now you integrate it backward. Okay. Then you will get the entire co-state trajectory also. So, now state trajectory and co-state trajectory as well as the previous control trajectory are available. Okay. The control trajectory may or may not be needed anymore, depending on the iteration that you are talking about. So, using all these, okay, you will be able to solve for the required control, okay, using the state equation, I mean this optimal control equation. Okay. So, this equation you are using it to integrate forward. This equation you are, so okay, let me summarize again. We are starting with a guess value of the control history. Okay. Then we are starting with a initial condition of the state. Okay. So, using this state and that control, whatever guess control you are having, you can integrate it forward. Okay, get an xf value and use that xf value and compute this lambda f. And once you have lambda f and the state trajectory also available, control trajectory also available for the entire duration, lambda f is available. Hence, lambda is a function of only lambda, all are explicitly available, and lambda is available. So that you can integrate it backwards and get the entire lambda history. Now, once you have state history and lambda history for the entire duration, you can go back and see whether this equation can be exploited further, and then you can, if there is any error, you can correct that and keep proceeding that way actually. Okay. So, that is the whole procedure of sorting method actually, sorry, gradient method. Alright. So, this is the procedure. Now, how do you do that basically? Now, we can go back to our derivation in the last class and then see the first variation of J bar. Okay. And the first variation of J bar is first expressed in this form, and hence we get all the necessary conditions, right. We got lambda f equal to del phi by del x f from here, we got lambda dot equal to minus del s by del x from here, we got del s by del u equal to 0 here, we got del x dot equal to del s by del lambda here. So, this is what your I mean what is our first variation of J bar. Now, coming back to here, we are assuming that the state equation is satisfied, co-state is satisfied as well as boundary conditions are satisfied. That means, this equation is satisfied, okay. This equation is satisfied, okay. This equation is satisfied, this equation is satisfied. That is what I mean what is not satisfied is this one. So, with respect to our the procedure, all these three are automatically satisfied. What is left out is this portion only. Okay. So, del J bar is nothing but this one only basically. Okay. Now, I have to compute a del u trajectory such that this del J bar has to go towards minimum value basically. So, using this concept of gradient vector and things like that, a natural selection is del u is negative of some factor tau times del s by del u again. Okay. So, ultimately if I select it that way, then del J bar turns out to be like this, and hence it is guaranteed to decrease actually. Del J bar is guaranteed to be negative. That's the whole idea of this gradient methods even in static optimization. We have seen that before actually. Okay. So, at every grid point of time will compute this delta u that way, and then update this control trajectory like this. The delta ui of t is nothing but that, okay, and that is already available, okay, and delta ui of t we just computed it that way. So, that is nothing but that, So, if I equate it to these two, then my updated control history is nothing but that. Okay. So, running grid point at time, I will be able to compute it that way. Okay. So, eventually if the procedure operates, then eventually it will keep on decreasing, and then finally it will become 0, and when it becomes 0, okay, del h by del u will also become 0, because this is a quadratic form actually. Okay. This can be 0 only when this del h by del u equal to 0. That kind of philosophy you can bring in and claim that, okay, if I operate the algorithm this way, then del h by del u equal to 0 will also be satisfied at the end of the procedure basically. So, this is the summary of the procedure. You can have already explained this 2-3 times. Assume a control history, integrate the state equation forward, integrate the co-state equation backward, and update the control solution. And while updating the control solution, it can be done 2 ways actually. Okay. One way is you can integrate it completely backward. Okay. Okay. You can integrate. Well, like let me just explain. You can integrate it completely Tf to T0 and then update it. Okay. But if you really want, Tf to T0, you can integrate this lambda equation backward, and then at a go you can update the control history. That's a possibility. Or while coming back, okay, in the backward integration procedure, at every point of time you can update the control, okay, right there, and then integrate it 1 delta t backward actually. Okay, then update the control there, and with the updated control you can integrate it 1 more step backward actually. Okay, so that kind of thing you can also implement actually. Okay, so these are the 2 choices that you have there actually. Okay. Alright, so this is what it summarizes, and then you have to repeat the procedure until convergence, and then convergence means this. Okay, as soon as this integral value is less than certain pre-selected constant, okay, then you can assume that it has converged and you stop actually. Okay, now the question is, how do you select this tau fellow? This tau factor, somebody can select arbitrarily, somebody can select 1 or initially 1 and later small value and things like that, that is also possible. But one way of doing that is, okay, at every iteration we can assume that it should reduce by some percentage alpha. The j bar should reduce by certain percentage alpha. I will select a tau in such a way that will result in that. Then I have a j bar value computed already before. Okay. So, I take the some factor, alpha is a percentage, so alpha by 100 is that. Okay. And then this one what I am looking at, tau into that has to be equal to that. So, tau can be computed that way. So, that way it is dynamically selected, different values for iterations, which will result in a pre-selected value of some percentage value reduction basically of j bar. Okay. That is one way, but again I am not emphasizing that every time somebody has to use it this way. Okay. You can come up with your own way of adjusting alpha as well. Anyways, before proceeding further, I thought we can think about some sort of exercise problem, and this is actually a challenging problem in a way. So, this has appeared in literature about 10-12 years back, around 2000 I believe, 90s and 2000, early 2000s and all that. Anyway, so this is the problem of some sort of like a air-to-air missile sort of thing. Okay, there is aircraft carrying a missile, it keeps on going. Okay, typically it is capable of firing a missile towards a target in front. Okay. So, if a target is actually in the backward and the back side of the aircraft, the typical thing is you do a cobra maneuver. Okay, you kind of increase your angle of attack, and hence the drag improves, drag increase and the speed reduces. So, you come back, okay, and then you reduce the angle of attack and then come down actually. Okay. If you increase the angle of attack, the lift is increased, so aircraft goes up, and the attitude also goes a little bit higher of thing, and then the drag is also more. So, it comes reduces the speed and all. So, it comes back, and then you decrease the angle of attack, and then you are back side of the target, and then you will be able to fire it actually. But in the procedure there is a lot of time is critical in such kind of applications. So, is it possible that you can still fire a missile in the forward direction, but the missile has to turn as soon as possible towards the backward and then engage on the target. Okay. So, the problem we are talking about is not engagement of the target, that is a separate problem, but what you are talking about is from release to exactly turning out, I mean turning in the backward direction, okay, by 180 degrees basically almost, okay, because this may not be exactly horizontal, it can have some positive angle of attack, I mean it can have some positive gamma rather, which is flight path angle. Okay. It can go a little bit ascending sort of attitude basically, and then it can releases, okay, then this has to turn in as less time as possible actually. Okay. Alright, also a small comment, other cases can be considered as a subset of this extreme scenario. If you want to kind of predefined some selected maneuver of not necessarily 180 degree, but anywhere lesser than that, then it is a subset of that actually. Mathematical perspective, it is actually a minimum time optimization problem, but that is typically difficult, and we will see that later. Minimum time problems are bang controls and things like that later, we will see that. Alright, now the system dynamics associated with that is given in this, given like this, where I assume that some of you will have this appreciation of aerospace problems, and this m is Mach number, and then gamma is flight path angle, alpha is angle of attack, thrust is TW is thrust and all that way. But this is also in a normalized form, okay, and there are various values, variables are given like this. So the system dynamics is already in normalized form, okay. So tau is these are derivatives with respect to tau, where tau is normalized like this, okay, and TW is thrust by weight, okay, that's kind of a normalized thrust sort of thing. SW is like this, and Mach number is by definition normalized, velocity of the vehicle divided by sound velocity. So using these variables, okay, you have this system dynamics, okay, and then our objective is to minimize the time taken, okay. So minimize the TF minus T0 sort of thing actually, and we have seen that the corresponding cost function, we have seen that J equal to this, so we can talk about T0 to TF, let me here, okay, T0 to TF 1 dt sort of thing. So TF minus T0, it will become like that. Okay, so we can do that, but it is done in a little bit different way, a little bit rather clever way, we will see that way. But also remember that due to certain engagement requirement and all, we cannot allow this vehicle to kind of this missile to drop velocity fast actually. So it's at the end of the turning, it should also have certain velocity, so that it can engage with the target in a good way. Okay, so and because remember while turning, this is also consuming thrust actually, and until engagement it doesn't burn thrust, it burns thrust initial segment and then proceeds with engagement and all that. So we cannot afford to lose too much of energy, because any turning also involves this induced drag and all that, it results in loss of energy. We cannot afford to do that. So there is a constraint for that MF has to be equal to 0.8 actually, okay. But we will instead of that equal to 0.8, we will tell approximately 0.8 is okay, and then this kind of a soft constraint is alright actually. So you put that as a soft constraint, it anywhere close to 0.8 is fine actually, that is the meaning. Okay. But if k goes to higher and higher values, then MF will go closer and closer to 0.8 actually, and this part will guarantee, okay, that minimum time is there, TF minus 0, that is TF has to be minimum actually, okay. But this is done in a little bit clever way. You can first use this is instead of tau as independent variable, we can think of gamma as independent variable, and first write dm by d gamma, dt by d gamma like that. And remember this 1 dt can be thought about something like this, dt is nothing but dt by d gamma into d gamma, and dt by d gamma is nothing but 1 by this dt by d gamma is available here, okay. So this dt by d gamma, this expression can be substituted here, okay, and then this MF minus 0.8 and all that is anyway available. So ultimately, because this equation comes to the cost function, whereas this equation becomes the system dynamics actually. So you have a cost function in this form subject to one scalar differential equation where independent variable is gamma actually, okay. So this kind of is a scalar sort of problem you can think about, where the m is the only state vector, okay, and gamma evolves from 0 to minus pi, okay, and this expression has already come here to in the cost function minimization part of it is already utilized, So essentially you minimize this cost function subject to this first differential equation actually. Okay. Alright, so I will leave that here, this problem. The assignment sense I seriously request all of you to attempt this, okay, using this some of these typical numbers actually. You can see some of these parameter numbers you can use and use some standard atmospheric data at the altitude of 5 kilometer. You have to select this atmosphere density, okay, and then proceed with all these numbers and then generate some results using this gradient method actually. Alright, so the last technique that in this class I want to talk about is quasi-linearization. It's a completely different approach again, and this also has its own beauty actually. Alright, so let us see that. I will not talk about a optimal control problem in general here, but we will increase the complex, I mean in generality sense, we will increase the generality little more actually. Okay. Alright. So, the differential equation in general we can talk about like this: z dot equal to f of zt. Now, z is nothing but x and lambda taken together actually. Okay. Boundary conditions, this includes a set of boundary conditions at different points of time. Okay. It can be only initial final time, it can also be something on the way as well basically. So, this kind of conditions are also possible. For example, some launch vehicle is there for going to moon, then you first go to a parking orbit and then go to a moon actually, right. So, that kind of thing it can be split either artificially or naturally, whatever way actually. So, the problem that you are talking about is this way: z dot is f of zt, where the boundary conditions are given that way actually. And we also assume that this vector differential equation has a unique solution over this time domain. So, the trick here is this nonlinear multi-point boundary value problem now. Okay, it is not necessarily only 2-point boundary value problem. This nonlinear multi-point boundary value problem is transformed into a sequence of linear non-stationary boundary value problems. Okay, and the solution will be found from there, and then it will approximate the solution of the true problem actually. So, how does it proceed? We will guess an approximate solution first. Okay, that is invariably that is the requirement. So, we guess an approximate solution z n of t n equal to 1 to begin with, and then we have to update the solution, and to update the solution we have to proceed this way actually. Okay. About this guess value whatever you have z n t, we can always write a linearized system dynamics, and that turns out to be like this, where by definition delta z n is nothing but z n plus 1 minus z n actually. This is available with us either as a guess or as a previous solution, and this needs to be found actually. Okay. So, this is like as I told before in the sorting method, this is like a time varying A matrix basically. So, you can always write it this way. Okay. Then we have to enforce the boundary conditions with respect to the updated solution. Remember, the guess solution need not have, but while we update the solution, our aim is that we should update in such a way that the updated solution should satisfy the boundary condition actually. So, how do you do that? Because then remember, this is the boundary condition. So, in this boundary condition I will substitute z n plus 1 here, and then I will see, okay, C of t I z n plus 1 t I, okay, inner product has to be equal to b I, that is the condition. But now z n plus 1 I can divide into that, these two, because that is the by definition is like this. Okay. So, I can write that this inner product is nothing but minus this inner product plus b I, because inner product can be split out actually. This inner product of a and b plus c is nothing but inner product of a b plus inner product of a c. So, using that I will be able to split that, and then I will be able to write that c of t I and z n of t I, this inner product is nothing but negative of that plus b I. Anyway, so where are we heading actually? Okay, that will be apparent in a while actually. So, what is that? From this differential equation delta z n dot equal to this, we will be able to write this way: delta z n dot is nothing but z n plus 1 dot minus z n dot. So, z n plus 1 dot is nothing but z n dot plus this equation, right, this a t times delta z n is this one by definition. So, I will substitute these two and I will write it that way. So, if you can interpret this Zn plus 1 dot has this homogeneous part a of t times Zn plus 1 plus this forcing function actually, which is already available with us. Okay. The previous gas history, previous gas solution is available with us, or previous solution or gas solution available with us. So, this is a forcing function and this is a homogeneous equation. So, if you really want to solve this, then we need a straight transition matrix again. So, this solution because it is a time varying matrix, we need a straight transition matrix, okay, plus a particular solution because there is a forcing function. Okay. Now, the straight transition matrix, as we know, it will satisfy the same differential equation with this boundary condition. So, this is clear. We can satisfy this differential equation with this boundary condition. So, you can integrate it and then get some updated values and all that. So, this value will be available with us. Now, what is not available is this one actually. So, let us see how do you get that. For getting the particular solution, you take the entire solution, full solution, and substitute it back in the original differential equation. Okay. And if you do that, this is what you are getting. This is the z dot sort of thing. Okay. Z dot is nothing but Zn plus 1 dot, and that is nothing but this kind of thing actually. Okay. I mean this entire thing basically. So, if you see this one Zn plus 1 dot is nothing but this whatever comes out from here, and remember this is a number, this is not a function, but this is a function and this is also a function. So, using that I will be able to write this left side of the thing, right side of the thing is anyway there, okay, this one plus this one. Okay. So, I am writing that. Now, what is happening here is this equation getting satisfied here, okay, this straight transition matrix will satisfy this equation anyway. So, this will get cancelled out actually, the first term will get cancelled out. So, you are left out with this term on the left hand side, where the right hand side will contain this one into that one here, and this one into the entire thing here actually. Sorry, this is only for that. So, this one into this one which is coming here and plus this one. Okay. Alright. So, this is how we get for the differential equation for this, but that is not everything. You also need a boundary condition for that. Okay. So, how do you compute that actually? So, that can be done this way, that you go back to this Zn plus 1 T0, okay, is given like this, okay, from here, and you substitute T0. Once you substitute T0, this becomes identity, okay, and then this is equal, this becomes Zn plus 1 T0, this is Zn plus 1 T0. So, this goes cancelled out. So, this is left out, this is left out. So, that is why you will get it 0 basically. So, Pn plus 1 T0 is nothing but 0, and Pn plus 1 dot is available from this equation. Okay. So, this differential equation and this boundary condition, if I integrate, I will get Pn plus 1 T as well actually, this one. Okay. And if I solve these equations, I get this one. So, now the solution is available basically, that one. So, this is how this causal elimination proceeds, and okay, the boundary condition for this can be obtained this way. You can put it, the boundary condition result you have to use it actually, right. So, you use it this way, okay, put it back, and then ultimately it results in something like this actually. This solution you can put it here, and then expand this inner product and take it that side actually. Okay. So, if you solve this, you will get a initial condition for Zn plus 1 actually. So, then you can you can integrate this equation. You need this Zn plus 1 T0 to get going basically. So, this Zn plus 1 T0 if you know, then if you know this and you know this, then you are done. Zn plus 1 T0 is obtained this way from the boundary conditions. Okay. Now, this one is obtained through this, and this one is obtained through this differential equation with this boundary condition. Okay. So, that is how you get the solution like this actually. Alright. So, this is the summary of this quasi linearization method actually. Now, this method is good under certain assumptions which are not that harsh actually. Okay. It can be shown that this sequence what you are getting it does converge to the true solution, and not only it converges, but also it converges at the something called quadratic convergence property. That means it can be shown that this property holds good actually. Okay. So, that means it converges fast actually. Okay. Remember, Newton-Raphson method of root finding typically satisfies this quadratic convergence. So, this kind of routine also satisfies this quadratic convergence property actually. More on that you can see this actually. See, this also is very interesting that furthermore for a large class of system it can also be shown that it converges monotonically. It does not overshoot and then come back and converge and all that. It converges from one side only actually, which is even nicer actually. So, even though the method seems a little bit more complicated and all that, I will still recommend that you can think of using this and then get a feeling. So, this is the corresponding small assignment problem. I mean we have again a scalar problem with a quadratic cost function, and these are some of the necessary conditions and all that. So, ultimately you will end up with this state and this co-state equation in this form, because control equation has been eliminated as a form of minus lambda, and you have these boundary conditions as well. So, the task is to solve this problem using quasi-linearization method. So, I seriously suggest all of you to kind of go to computer programming and then try to code these algorithms and then have a feeling of how these algorithms operate to yourself actually. Some of these references for numerical methods I have taken from this, and largely this gradient method and quasi-linearization I have taken from this book. A very good book for classical solution of optimal control problem. So, that is the D. Kirk book actually. Then all other things are available for for especially the shooting method. You can see this. Okay, this is actually a good book also. Okay, 2-point boundary value problems. It essentially meant for 2-point boundary value problems only actually. Okay, so there are various other things that the book talks about. The entire book is meant for that actually. And again, as I told in the very beginning class, Bryson and Hugh is always a standard book. You can refer to many of the things there. Sage and White is also a good book. And these are some of these classical, very good well written papers rather. It is a very old paper, and this is not that old, but it is also relatively old. But these are very well written papers where you can see a lot of these ideas there in a good way actually. That is all I wanted to talk in this particular class. Thanks a lot.